All right, so my name is Sean Harris,
I'm Ian Neitz.
and we're presenting the Pintler Peaks Slope Instability Investigation and Design on behalf of the Department of Geological Engineering at Montana Tech. Our site is located approximately 1 mile west of Anaconda, Montana. It's underlain by some colluvial sediments with weathered volcanic bedrock. There's a slope instability on the site that was created by residential excavation for home construction. The slope instability was recognized in 2018. With more obvious tension cracks in 2019. And since then, the slope instability has involved more than 20 feet of downslope movement, as well as 8 feet of subsidence in certain areas. The clients for the site, being the residential homeowners in the area, observed significant groundwater discharging at the toe of the slope. And were concerned about the origin and relation of the groundwater to the slope instability, and thus sought the help from Montana Tech to do an investigation.
So the project objectives for this were to characterize the underlying cause of slope movement. The clients came to us with a want of understanding for the causes of the landslide, and that's what we were trying to provide. So we designed a comprehensive site investigation, laboratory testing program, and a modeling effort. We wanted to implement as many portions of that design as we could. So we weren't really going to design mitigation, but we were going to design the investigation. So we wanted to really do our best to give these clients some useful knowledge in the driving factors of the landslide. So, and that all pertained to groundwater discharge, toe excavation, and further development on the site. So they were really looking for an understanding, and that's what we were trying to provide.
On our site, we utilized 3D modeling via drone imagery. We flew a series of flights from a pre-programmed flight pattern. So the drone was in the same position in the sky at each week we flew, generating essentially the same model. And using that same model in our software, Pix4D, we were able to compare between the models and detect changes in the slope appearance, such as widening and lengthening of tension cracks, as well as we were able to detect some new tension cracks.
The next portion of the project involved a comprehensive site investigation. This had a surface and subsurface component. The surface investigation included measuring a superficial slope profile, collecting hand samples from superficial materials and then excavated materials that have been removed from the site, observing tension cracks and installing monitoring devices for the tension cracks, and then measuring groundwater discharge as it was coming out of the toe. So looking for variable amounts of discharge over time.
Our subsurface investigation involved both geotechnical drilling and the observation of a toe excavation. The homeowner had removed more material to prevent this slope toe from impacting his garage. So they removed about 1,200 cubic yards, and we were on site to observe that. And with the geotechnical drilling, we were able to run some standard penetration tests, do some lithologic interpretation, as well as collect samples using a Shelby tube in a weak layer that we later defined as a montmorillonite clay, and eventually install piezometers in each of these holes, just PVC piezometers, to measure head of the groundwater table. And then we did run some homemade PVC inclinometers down those holes to try to detect if the slope was moving at depth. The two boreholes we drilled had respective depths of 29 and 15 feet, and they're on this figure below. The piezometers were installed, which helped us calibrate our water table into our models. And then we went on to install one hand augured piezometer at the toe of the slope in the area that was discharging the most.
The engineering characteristics of these materials were classified with the superficial materials as a well-graded sand with clay. And then we identified the suspect weak layer at a depth from our drilling at 16 to 18 feet. That was the interval which we sampled for later materials testing with a direct shear test. That direct shear test yielded the weak layer with a cohesion of 100 PSF and a friction angle of 25 degrees, which was lower than any other samples we tested. The mineralogy of these layers and these samples were all tested using XRF, XRD, and shortwave infrared to identify some mineralogy with those layers.
After our site investigation and materials testing portion was complete, we moved into traditional slope stability analysis using the program Slide 2 by Rock Science. This involved both geotechnical and groundwater components. We uploaded our slope profile into Slide and used limit equilibrium methods, specifically Bishop, Yanbu, and Spencer methods, analyzing circular failure methods to determine the factor of safety for these areas. We chose to analyze circular failures based upon the nature of the slope movement, the tension cracks, and the toe bulging up over onto the driveway was indicative of a circular failure. The groundwater model was developed in conjunction with the geotechnical model, all in Slide, which made for easy comparison to what was going on in the real world. The groundwater model utilized finite element analysis for total head modeling.
The piezometric surface was calibrated to equal the discharge that we were getting out of the toe of the slope. So our water table was calibrated until we were able to effectively match the discharge coming out of the toe of the slope at 1,300 gallons per day. And so we ended up with a model with discharge of 1,345, which was going to slightly overshoot what we were seeing for discharge out of the toe to kind of account for seasonal fluctuations. So we were doing this study at a low water time of the year. So we did want to bump that up by about a 30% margin to account for what a spring runoff situation would look like. Our analysis suggested critical factor of safety values between 0.74 and 1.2. And that was on two separate failure planes. So we had an upper failure plane and a lower failure plane. The upper failure was associated with the road cut. And we did see separate tension cracks forming on that uppermost portion. And then the lower section of the slide, which is the most actively moving portion, is where we saw our lowest factor of safety value of 0.74. And that is as it is moving every day towards this gentleman's house at the bottom. So a factor of safety below 1 in this case for us, even though it is well below 1, does reflect what we're seeing in the field of a currently failing slope. Sean?
So in the end of our project, we were able to offer some conclusions and recommendations to the clients. We concluded that we achieved a realistic characterization of the site in our modeling and our materials characterization. Our models were appropriately calibrated to reflect those field observations. Our clients gained an understanding of the nature of the slope instability. Mitigation alternatives were suggested, but not designed, such as dewatering, soil anchors, retaining walls. And then we were able to recommend that monitoring of the water levels continued year-round with seasonal fluctuation to get a better understanding of this potentially perched water table. And then we also recommend that the clients ultimately should secure the services of a professional engineer to design some mitigation alternatives.